So now we have been studying the principles of communication systems, module 3, and first we studied the basic noise, and then the noise in the DSB-SC, then noise in the AM receiver, and then we studied the noise in the FM receiver. So today we'll take up numericals corresponding to noise in the frequency modulated receiver, and also we'll consider what is known as capture effect, and then what is known as FM thresholding effect, and then the pre-emphasis and de-emphasis. So we have studied the FOM, that is the figure of merit for the FM to be equal to 1.5 beta square, where beta is del F by FM. This is the formula, right? And that formula we can study from here also, right? So list of formulas are there. FOM for amplitude modulation, FOM for frequency modulation, 1.5 beta squared. Then general definition for FOM is SNR output divided by SNR channel, and this can be written in dBs also as SNR 0 dB is equal to 10 log SNR 0, and SNR CdB is equal to 10 log SNR C. So we have already seen the numericals associated with the noise in AM. Today we'll take up the numericals in the noise for FM. So an FM signal with a maximum frequency deviation of 75 kilohertz is considered, and this is applied to a FM demodulator when the input channel SNR is 15 dB and the modulating frequency is 10 kilohertz. Estimate FOM and SNR at the demodulated output. So FOM, we know that it is 1.5 beta squared. Beta is nothing but del F by FM. Del F by FM. And maximum frequency deviation, that is del F, is given as 75 kilohertz. So therefore, we are writing here 75 kilohertz. And the modulating frequency FM is 10 kilohertz. And this is what we are writing over here. And hence, we'll get beta is equal to 7.5. So the figure of merit will be 1.5 times the beta square, that is 1.5 times the 7.5 squared, and that will give us 84.375. Now this FOM is nothing but the SNR O divided by SNR C, and we are given the value of the SNR C as 15 dB. Hence we need to find the SNR at the demodulated output. SNR at the demodulated output. So O, SNRO is what is to be found. But what is given in dBs, and hence we should take the FOM in the value of dBs or vice versa and try to find out the value there. So SNR C in dBs is what is given, 15 dB, and we can convert that into the normal value. SNR C is equal to 10 to the power of 15 by 10. That 15 is the dBs, and that will give us 10 to the power of 1.5. That is 31.6227 will be SNR C. FOM is calculated as 84.375, and if you substitute that in the relationship which is over here, SNR 0 will be FOM into SNR C. FOM is nothing but 84.375. SNR C is calculated as 31.6227, and that will give us the value which is 2668.16. And that has to be again converted into dBs by taking 10 log of the corresponding quantity. 10 log of the corresponding quantity, and that will turn out to be 34.262 dBs. In terms of dBs, the output signal to noise ratio for the demodulator will be this much. Now let us go to the next problem. An FM receiver receives a FM signal. St is equal to 10 cos 2 pi 10 to the power of 8t plus 6 sine 2 pi 10 to the power of 3t. Calculate the figure of merit for this receiver. So St is equal to 10 cos 2 pi into 10 to the power of 8t plus 6 sine 2 pi into 10 to the power of 8t. And the same St in the general form is AC cos of 2 pi fct plus beta sine of 2 pi fmt. So AC is 10, FC is 10 to the power of 8, beta is 6, FM is again, 10 to the power of 3 here. This is 3 over here, 10 to the power of 3 over here. This is 8 and this is 3. So the value of beta is 6 and figure of merit is 1.5 into beta square, that is 1.5 into 6 square, that will give us the value 54. So that finishes the numericals within the noise in FM. Now we'll go for the capture effect. So here we are trying to see what a capture effect is. In general, whenever two modulating signals are near to each other, then it becomes very difficult for the demodulator to find out which is the what you call modulating frequency which it should lock to. Say if one of the one of the frequency is the modulating signal and the other which is nearer to it is noise, then again whichever signal is more powerful, that will be caught or locked by the uh, you know uh, FM demodulator. And hence, say if the noise is greater than the FM frequency modulating signal, then that will create a problem. So in FM systems, the signal can be affected by another modulating frequency modulated signal whose frequency is close to the carrier frequency of the desired FM signal. So then the receiver may lock such an interference signal and suppress the desired FM signal, and the interference signal becomes more stronger than the desired signal. So when the strength of the desired signal and the interference signal are nearly equal, so when we say that the strength of the desired signal and the interference signal are nearly equal, the receiver locks to the interference signal for some time and desired signal for some time. So, this will be the complication if they are of, same strength. Then for some time it will lock onto the interference signal, for sometimes onto the desired signal. And this goes on randomly and the receiver captures the stronger signal. So if the interference is stronger, then it will catch that. And this effect is known as the capture effect. Okay. So for the definition, we can write this rather than the above one. So let us go to the FM threshold effect. The SNR 0 of an FM signal is valid only if CNR measured at the channel signal to noise ratio measured at the frequency discriminator input measured at the frequency discriminator input is very much greater than unity. If SNRC is very much greater than unity, or CNR is greater than the unity, then we can use the formula for SNR output as we have got it, 3AC squared KF squared P by 2N0 W squared. If CNR is less than 1, then the FM signal is corrupted by the noise and FM receiver breaks down. And this is called the threshold effect of FM. So CNR should never be less than 1. It should always be greater than 1. So threshold effect is defined as the minimum carrier to noise ratio. CNR is the minimum carrier to noise ratio that gives SNR 0 not less than the value predicted by the usual SNR formula, assuming a small noise power. The threshold effect can be avoided by keeping the carrier to noise ratio of FM signal greater than 1. So CNR is the carrier to noise ratio, and that should be greater than 1. When CNR is less than or equal to 1, FM receiver breaks down due to the thresholding effect, and this point is called as the thresholding point. CNR equal to 1 is called as the thresholding point. So how do we reduce the FM threshold? FM threshold can be reduced by using the FM demodulator with negative feedback, or by using what is known as phased lock loop demodulator. Such devices are referred to as extended threshold demodulators. Extended threshold demodulator. So somehow we should reduce the FM threshold effect, and that is done by means of the negative feedback, or what is known as phased lock loop, wherein we will try to use a VCO in place of a local oscillator. This type of FM demodulator is also known as FMFB. FB here is referring to feedback. So frequency modulated feedback demodulator with feedback demodulator. So rather it is negative feedback, or you can also call it as phase lock loop, because we are using the VCO in the feedback. So this figure shows the block diagram of FMFB demodulator, where we are using a mixture, the BPF, band pass filter, frequency discriminator, the baseband LFF, and the output is connected back to the VCO. Through the VCO, it is connected back to the mixer. So in place of the local oscillator, we have the voltage controlled oscillator. So the instantaneous output frequency of such VCO is controlled by the demodulator output signal. So VCO's input itself is the demodulated output signal. The bandwidth of the noise to which the FMFB receiver responds is precisely the band of noise that the VCO tracks. Thus, the FMFB receiver acts as a tracking filter that can track only the slowly varying frequency of the wideband FM signal, slowly varying frequency of the wideband FM signal, and that just corresponds to the baseband signal. Therefore, it responds only to the narrow band noise. So the VCO responds to the narrow band noise centered around FC. As a result, FMFB receiver allows a threshold extension up to 5 dB to 7 dB as shown in the figure. So this is the actual threshold. This is the extended threshold by 5 dB to 7 dB. So that gives us the difference over here. And this just corresponds to the output signal to noise ratio versus the carrier, noise ratio CNRD. So therefore, FMFB demodulator with negative feedback provides 5 dB to 7 dB enhancement in the CNR, and it always maintains CNR greater than 1, and it avoids the FM threshold effect. It avoids the FM threshold effect. Next, we come to what is known as the pre-emphasis and de-emphasis. So again, pre-emphasis and de-emphasis methods are commonly used in the FM transmitter and the FM receiver respectively to improve the threshold, and ideally that just means that to improve the noise performance. So the pre-emphasis and de-emphasis are simple RC networks used to improve threshold up to 13 to 16 dB. The earlier figure, which is there over here, earlier one improves only by 5 to 7 dB. Whatever we have used here using VCO, but using the pre-emphasis and de-emphasis, we can use, improve the threshold up to 13 dB to 16 dB. So figure 1 shows the FM transmitter with pre-emphasis filter having transfer function H3F. So this is the pre-emphasis filter, and this is the FM demodulator, and we'll get the pre-emphasized FM wave output signal. So that is basically a high pass filter or a differentiator. High pass filter or a differentiator. So pre-emphasis circuit is a high pass filter with transfer function which is shown over here, right? So what it is doing is higher frequencies are, so to say, amplified, lower frequencies are, kept as it is. So as the frequency is increased, the signal gets more and more amplified. At higher frequencies, you have more gain. At lower frequencies, you have lesser gain. So to improve the SNR output at the FM modulator, the high frequency components of the message signal MT are artificially emphasized. Emphasized just means amplified at the transmitter before the modulation process as shown in the figure 1. So this is the pre-emphasis, that is increasing the amplitude of the signal by means of having a H pre-emphasis F value. So after pre-emphasis, MT occupies the entire range of bandwidth assigned, and then all the frequency discriminator. Then at the frequency discriminator, FM demodulator of the FM receiver, inverse operation of the pre-emphasis, that is known as de-emphasis, is performed. So by this, the what you call noise gets reduced at the higher frequency. So figure 3 shows the FM receiver with de-emphasis filter having frequency response HDEF, and this HDEF is inverse of the H pre-F, mod of H pre-F. So de-emphasis filter per circuit is used after FM demodulator, as shown in this figure, wherein you have the signal here and the noise over here, both are joined together and given to FM demodulator, and whatever the FM demodulator is given, and that is given to the de-emphasis filter. So we'll get the de-emphasized output signal. Whatever is emphasized should be reduced, brought back to the same value. So de-emphasis circuit is basically an integrator, RC low pass filter or integrator as shown in the figure over here, whose response will be like this. That is, higher frequencies are reduced in amplitude or de-emphasized now. So high frequency components presented the output of the FM demodulator output signal are de-emphasized to restore the original message signal power distribution. So during de-emphasis process, high frequency component of the noise are also reduced and thereby efficiently increasing output signal to noise ratio SNR 0. The frequency response of the de-emphasis is, generally pre-emphasis and de-emphasis are related by H pre-emphasis is equal to 1 by H de-emphasis. And that is H de-emphasis will be 1 by 1 plus JF by 3 dB, and H pre-emphasis will be 1 plus JF by 3 dB. So the effect of the de-emphasis filter on the output noise is illustrated in this figure. Now this just gives us, the signal to noise, so to say, this is the power spectral density of the output noise spectrum. It is high at the higher frequencies and low at the lower frequencies corresponding to the output. Hence, we try to do the frequency response of the de-emphasis filter, which is magnitude is reduced over here, and the reverse of this is taken at the pre-emphasis filter, that is higher frequencies are emphasized, and thus we will get the better noise spectrum, which is equivalent to this itself. So figure 5.A shows output noise spectral, which is the parabolically increasing towards the edge of plus or minus W. Therefore, SNR output reduces before the de-emphasis. When noise is filtered by using de-emphasis, filter having frequency response shown in figure 5B, the output noise spectral of the de-emphasis becomes almost flat at plus or minus W hertz as a result of SNR 0 increases and it avoids the FM threshold. So pre-emphasis and de-emphasis circuits are effectively used to increase the SNR at the transmitter before modulation and receiver after modulation of the FM system respectively. Now this can also be explained with respect to the figure over here. This is the pre-emphasis and this is the de-emphasis over here. I think the graphs we have not put. So this is the SN0T and this is the SNF. That is the what you call for the de-emphasis. This is for the what you call pre-emphasis figure, as well as the noise also. Noise is of this shape. So it's better that the same shape is brought for the signal also, which is flat, and that will give us that both are of same shape, and hence we can reduce it at the output. Now this figure gives you all the graphs corresponding to that. You can see that this is the SN0F, and this is the A is just gives you the power spectral density of noise at the FM receiver, and this gives you the power spectral density of the typical message signal over here, typical message signal over here. That is at high frequencies you have the high value over here, and this is to be basically emphasized. Whatever message signal is to be emphasized at the input end, so that it becomes flat like this, and later at the receiver it can be de-emphasized, so that it comes back to the original shape, which is like this. Okay.